We're going to hear now from Pow.Bio. We have Ouwei Wang, who is the CTO and co-founder of the company. He's going to be telling you about self-driving bioreactors, practical AI for modern biomanufacturing. Ouwei.
Hello. Good afternoon. The slide gonna be there. Great. Hi, everyone. Good afternoon. My name is Ouwei Wang. I'm the CTO and co-founder of Pow.Bio. We are a California, US-based company that provides intelligent biomanufacturing services to the synthetic biology industry. We help other companies to produce the first gram to kilogram amount of material, and we help other companies to optimize their bioprocess as well. We have a strong tradition in internal R&D with a focus on continuous biomanufacturing and the digital twin technologies, and how we're using these digital twin softwares to further amplify our productivity in continuous, which is something I'm very excited to share with you about. So, biomanufacturing is kind of a fascinating topic, right? This need no introduction here. You basically use engineered cells, mix that with some carbon source, and boom, basically products come out, like modern day alchemy. But if we were to be honest with ourselves, right, like biomanufacturing in 2026 is still kind of highly artisanal. So we have bioreactors that, like million-dollar bioreactors that run by Excel files and gut feelings. We have PhDs that kind of squint at the trend lines in the middle of the night to decide whether we should bump the fit rate by 10%. We call ourselves scientists, but fundamentally, like sometimes, honestly, it feels like more of like an artisanal craftsmanship. The fundamental problem is that for any device that is built for human operators are limited by humans' cognitive bandwidth, right? On a good day, when I'm not like super jet lagged and really overdosed myself on caffeine, maybe I can hold like 7 to 10 different things in my head, in my working memory. But when you're running bioreactors, and especially if you're running like a fleet of bioreactors, you literally continuously getting assaulted by like 100 different variables. And then as human, what can we do? Well, we simplify, right? We simplify and make decisions based on whatever variables that we can understand, but that's kind of the problem because there are a lot of insight can be missed, and then people can also make mistakes. That's why we have high batch-to-batch variability, why tech transfer among facilities often fail, and scale up can be, the result of scale up can be unpredictable and challenging. So one way to solve this, many people probably thought about this, and you probably thought about this, is to use AI, generative AI, to run the bioreactors, right? So AI doesn't need to take smoke break, it doesn't need to take lunch break, it can just keep running 24/7, nonstop, read every variable, every minute from every bioreactor simultaneously. But the challenge with AI is that, and you probably thought about this too, right? Like it hallucinates, and sometimes it hallucinates like very hard. It is one thing that, you know, it makes mistakes when you're drafting emails versus when we're like really operating large machineries. If it start to hallucinate and make mistake, A, it can be really expensive financially. B, even worse, that some catastrophic error can cause personnel injuries, which is something we absolutely do not want. So we cannot put agentic AI directly on top of a reactor. What can we do is that we can put a digital twin layer to bridge the gap between the digital world and the physical world, where the AI lives in the digital world and us, and then the bioreactors lives in the physical world. So basically, the agentic AI kind of work with the digital twin, and digital twin helps to set the boundary of this agentic AI. It simulates physics, chemistry, biology, and operation. So if the recommendation from agentic AI does not survive contact with the digital twin, it will definitely not reach the bioreactor, and therefore ensures the safety of the operation. And with this setup, right, we can run 24/7 closed loop optimization with agentic AI generating and identify insights that takes hours and usually which take human potentially weeks. This is not 5 years into the future, not 1 year into the future. It's what we have now in our facility. So we have, because we don't have a lot of time, so I'm just gonna very quickly go through some of our workflow. This is one of our workflow, which is just for process optimization. Fundamentally, we have a specialized team of agents that specialize in different stages of this process optimization. So first, we have model build, right? Like basically use an agentic team to gather past data and use that to mold into our very first initial model of the bioprocess. And of course, we have some human-crafted model as a reference template as well. So after that, step 2 is model fit. So this is actually already using AI to drive the reactor in real time, which I have a slide to share as well, so that the agentic AI dynamically changes the conditions in a continuous bioreactor to gather new conditions and the information to fit the biology part of the model. So really understand the response surface and the behavior of the strains in the bioreactor. Third is, the third stage is in silico optimization. So this is basically like a virtual experimentation after we lock down the biology, and we basically say this is kind of what we think the biology will behave in the bioreactor. Can we optimize the operation? Can we optimize the bioreactor volume, the initial volume, the final volume, the inoculation volume, feed rate, etc., things like that. And then the last step is deployment. So basically autonomous AI-enabled autonomous bioreactor operation, and importantly, having all its recommendation fact-checked or validated against a digital twin to make sure that there is no safety problem. Here is some real data. So we generated this honestly just a few weeks ago. The experiment basically starts on Friday and it goes over the weekend, and on Monday we just come to the lab and analyze the result. So on the left you could see basically just showing the model prediction versus the actual outcome. On the y-axis you'll see basically predicted response, and the x-axis seeing the actual response with the R-square of 0.9. So this is pretty good, I would say, that for this model that be able to predict the productivity of this given bioprocess. And on the right is kind of like the journey of the bioreactor over the course of the reaction. So basically it starts at a place, and over time taking, I think in this example, it took 33 different steps to really solve the response surface so that we know what is the best feed rates that gives the best, the most optimal production cost. So because it's a simulation, right, we also have the ability to carry out virtual experimentation to really identify what is the best combinations of feed rates. So in this example, this is just like a 5 by 5 by 5 kind of condition sweep to identify some trade-offs between a given bioprocess, and using this to identify like what is the best production economy that we can achieve for this given bioprocess. And lastly, and this is the most important slide, which is kind of how we are using our software at scale to produce 25 kilograms of lactoferrin over 300 hours and over in a 3,000 liter reactor. So in this process, kind of the chart is kind of not super interesting, just total lactoferrin product produced over time. And basically the runs, which is the green line with our digital twin, produce the most lactoferrin. But honestly, if you double clicked into this and peek behind the curtain in some way, I guess, to really see the detail. So what happened was in the actual run, during the actual run, we had a mechanical failure at the condenser. So in doing this continuous fermentation process, we basically lost control of volume. Because we lost control of reactor volume, we also lost control of biomass density, of product titer, and because of that, we no longer know how fast to feed. We basically no longer understand our reactor. So basically, we took all this information and to our digital twin and be like, hey, so this had happened. The condenser is broken, and we are having all these problems. Can you help us to generate a procedure so that you can call this counterfactual intervention or kind of like soft landing procedure, but tell us what to do so that we can actually continue to enable the success of this run. So basically, the digital twin basically gave a list of recommendations, including increase the filtration rate, decrease or different dials, and increase feed rate, things like that. So we're able to actually successfully finish this this process. So yeah, so we're looking for alpha testing partners. So if you have questions, if you're curious, if you're wondering if this process can be beneficial to your process, please keep in touch. And my schedule is pretty open for today and tomorrow. So if you're using the app, feel free to reach out as well. So thank you.